Welcome back to the second part of Chapter 31. This is our final video, video 3 for part 2 in Chapter 31. And we're going to look at radiation detectors. There's such a wide variety, I thought I'd hit the high points. So all detection techniques work on energy loss by the radiation in the detector. So the radiation has to actually pass through the detector for it to be detected. The earliest form of detection was photographic film, and we still use it today. With any kind of photographic film, whether it's an emulsion on a piece of glass like they used in the beginning, or plastic films that are available today, what happens is when the radiation penetrates it, it fogs the film just as if light has hit it. And the amount of exposure that's indicated when you process the film tells you how much, and in some instances, what kind of radiation you've received. Film badges are used in all kinds of labs and hospitals to look at cumulative doses over a period of time. Typically, you'd have a film badge, and once a month it goes off for processing so that your employer can keep track of your cumulative dose of radiation that you've received on the job. A lot of times you'll see them pinned to people's collars. They're not very big. They're maybe an inch long by 3/4 of an inch wide. And it's just a little plastic clip-on thing. So sometimes you don't want to wait a month to get your reading. You need an immediate answer, and that's where dosimeters come in. So dosimeters are little electroscopes. So what happens is the radiation enters, the dosimeter looks like a fat ballpoint pen, and it's roughly that size too. So they clip on you. You usually have at least 2 of them. Normally you put them somewhere on your mid body. You wouldn't stick them down in your socks or up in your hair, but in a pocket, either in your chest pocket or a pants pocket, somewhere mid torso is usually where it's done. But when the radiation enters the electroscope, what it does is it ionizes the air, which will discharge the electroscope. So slowly over time, as radiation passes through, the reading on the dosimeter changes, and that indicates the amount of radiation that you've received. So again, looks kind of like a fat ballpoint pen. And what you do is you hold it up to the light and you look in one end of it, and that's where you see the scale. So you can see 0 is over here on the left and it moves to the right. So if while you're doing a particular experiment in the lab, you're concerned, you've gotten exposure for some reason, you could take your dosimeter out of your coat pocket, hold it up to the light, and get an immediate reading. And typically both dosimeters that you carry with you agree with each other. If there's a big discrepancy, you worry that something's wrong, maybe with the dosimeter itself. So another type of detector is the Geiger-Müller tubes, or the GM tubes, or Geiger counters. People hear about these all the time. So with a Geiger counter, what happens is the GM tube is a lot like the dosimeter. The radioactive source enters in, it ionizes the gas that's inside, and this produces a charge which is measured. It goes to something called a rate meter, and a rate meter typically has a dial on it so you can see the numbers. But more helpful than that for most people is it usually makes a sound. These are the kind of things where if you're carrying them along, you hear tick, 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 tick. When I was in graduate school, my major professor would say, you want to, when you're in the lab with the nuclear accelerator, you want to listen for what he referred to as the Hall-ass rate. And I said, what is that? And he said, oh, you'll know it when you hear it. And obviously it means when the sound goes from something constant, you know, tick, 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 to tick, 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 tick. When the sound starts going crazy, then you need to stop what you're doing and leave immediately, which is why in a lab, these things are oftentimes just in the background running, just as a way to monitor what we call background radiation. We'll talk about that in the next chapter. You can also have a scintillation counter. This can use a solid, a liquid, or a gas that scintillates or gives off light when struck by radiation. And so the amount of light that's given off indicates the type and the energy of the radiation. Sodium iodide is a really common scintillating material, and it's very effective in detecting gamma rays. So scintillation counters are hooked up to computers. Whatever sample you got goes inside the machine. If you're using a liquid, sometimes you'll use it for biological materials where, like, if you're worried about the radiation being given off by a leaf, you would put it in a little bottle with the scintillating material, and then all your little bottles go chugga, chugga, chug in the detector, and then the information is sent to the computer. And you can look at your output later. So you can also have semiconductors. These are really tiny. They're like the size of a dime or smaller than that. And the radiation, when it passes through, again, produces a current, and that produces changes in your semiconductor, which sends an electric signal to a computer, and it's analyzed and tells you how much radiation you've received. One that's more fun is a cloud chamber. So cloud chambers have a supercooled gas that is cooled just below the condensation point. If you're doing it in a lab, like a physics lab for educational purposes, you might put rubbing alcohol in your container and let that vaporize, because rubbing alcohol vaporizes very easily. It'll vaporize at room temperature. And so to supercool it, what you do is, if you have it available, you put it on a block of dry ice. If you don't have dry ice available, sometimes there are other techniques. So what happens is that when the radiation passes through, it ionizes the gas molecules, and these ions act as condensation nuclei for the vapor. And the little vapor molecules are attracted to those ionized gas molecules, and they form little vapor trails, like the trails that an airplane leaves in the sky overhead. It's the same kind of process. So the shape and the length of the trail is going to give you an indication of the type of radiation and its energy. I will put a link to this video in the assignment so that you can see it. It is kind of neat to see it in real time. So we'll put the video link. So here's a drawing where you've got your dry ice, and it's super cooling your container that has radiation in alcohol vapor in it. And then there are two ways that the material, the radioactive material, gets inside. If we were doing it in lab, we might have a needle that we could stick down inside this that's been dipped in a radioactive material. Or if you're looking at just background radiation, cosmic rays from deep space can enter and cause trails. This is a photograph of a larger cloud chamber. These little straight lines that you can see going across are cooling wires. They act to help keep the interior cool. And these little smudgy looking, it looks like it's dirt and needs to be cleaned, but these are the vapor trails that you look at. So some of them are straight, some of them curl just a little bit. you get a variety of things. You can employ a similar process with a liquid, and instead of making a cloud trail, you can make a trail of bubbles. This is called a bubble chamber. They usually use liquid nitrogen for that, kept very near its boiling temperature. And again, as the radiation passes through, it ionizes, and then the bubbles form along those trails. Here is a photograph of one. You can see some of the material is very energetic and goes straight through. Some of the material curves out and around. It's amazing what you can tell. This one's done some really funky stuff as it moved through. So each one of these little white trails indicates the path that a particular type of radiation traveled along as it moved through the bubble chamber. And the last type we'll mention are spark chambers. So in a spark chamber, you basically make little visible sparks. When your particle enters again, they ionize the gases and then sparks appear. So just a variety of different ways that you can detect radioactive decay. So this is going to stop our video, and we're finished with chapter 31.